This will be the second video on volumes of revolution, this time using what's known as the washer method. And our goal? Calculate the volume generated by revolving a bounded area between two curves around an axis, which is contrasted with what we saw with the disk method, where we were just revolving one curve around one axis. You'll see a lot of similarities between the two methods, but there's one little issue that this method is going to help us resolve. Here's our scenario for this video. A curve f of x models the outline of the top half of a ball, which sounds very similar to where we were in the last video. So here we are with our f of x curve, and a cylindrical hole of radius g of x is drilled through the center of the ball. So a perfect cylinder, we're just going to imagine looking at coming across the center of where the ball is with this nice straight line g of x. And the question, what is the volume of the resulting object? Originally, to make the ball, we were revolving this entire region bounded between f of x and the x-axis around the x-axis. But now, if we're going to take the hole out of the middle of it, really all we want to revolve is this region right here. And what we don't want is this space right here that we are going to drill out from the center. And so I'm going to go back to how we set up the volume of revolution in the last video. What I'm going to think about is a representative rectangle that I could draw that would be getting revolved around this x-axis. Imagine this like swinging a rope at the end of your arm. If I keep making little cross sections like this, I can model revolving this region and creating this ball. But what's happening in this problem is a little bit different. I have one region of my representative rectangle that's going to represent the solid part of the ball, right here. And I have one region that's going to represent what is getting drilled out of the center, the volume that will no longer be a part of my resulting volume. And what I'm creating now is not one solid disk, rather it's a disk with a hole in the middle. Or a washer. You can also think about it, not sure what a washer is, think about it like a donut. We've got a solid piece, and we've got some open air here in the middle. But the one thing we have to be aware of is, just like with the disk, it's not just a flat circle with a hole in the middle. This has some height to it. And we're going to go with the same process we went with for the disk method. If we can describe the volume of this washer, finding the volume of the entire resulting shape, the ball with the hole drilled through it, would be adding up many, many smaller volumes. So what we'll think about is, this washer has a height. The thing with this washer that's a little bit different is it has a radius, but it actually has two of them. It has a big radius and a little radius. The radius for the entire disk, if I didn't have the hole in the middle, and the radius for the part that I don't want. Well, the big radius, the radius of the entire shape, would be the distance from the x-axis up to the topmost curve, or f of x. And the little radius would be the part I'm getting rid of, in this case what I called g of x, the radius of that cylinder that I'm drilling out. And if you think about this as just working with areas, how I would find the area of the circle with the hole would be to take the area of the entire thing, pi times the big radius squared, and subtract off the smaller circle with the smaller radius, pi times little radius squared. Or in terms of our functions, we would have pi times our outer function squared minus pi times our inner function squared. And the height for this washer would be some small change in our x values. So in order to make a volume for one washer, it would be pi times the big radius f of x squared minus pi times the little radius g of x squared times dx. And to get the volume of the entire resulting shape, I would add up all my smaller volumes. I would add up every single one of these that's formed across the entire region that I care about. The big thing is the boundaries. And the boundaries, we call them A and B, are where f of x equals g of x. And that would tell me where to start and stop my region. If you just let yourself go one step further on this, notice that you could factor out a pi from both of those expressions, from both areas, and move that constant to the outside of your integral, and we would get pi times the integral from a to b of however we're defining our big radius squared, in this case f of x, minus however you describe your little radius squared, or g of x, times dx, the width of that washer. So conceptually, we are taking a volume of revolution minus a smaller volume of revolution that we want to remove from our 3D object, and ending up with some revolved shape that's going to have a hole in the middle. And that'll do it for the concept of the washer method for finding volumes of revolution. Thank you for watching.